Welcome back to the study group. So in this video I will be covering the algorithm to find or to solve the questions which of the topics which we covered in the past 3 videos. So starting with vector spaces. So first topic is to convert a matrix to row echelon form. So check the entries below the first leading entry. If they are non-zero, then convert them to 0 using row transformations. Repeat this process till all the conditions of row echelon form are satisfied. Next is to find rank and nullity and check the invertibility of a matrix. So first convert it into row echelon form. Then by the row echelon form, we take the rank as the number of non-zero rows and nullity as the number of 0 rows. So if it is full rank, then it is invertible. That is, nullity should be 0. There is another method of finding the rank, which is using determinants of submatrices. So consider the largest possible submatrix, find its determinant. If it is non-zero, then the rank is size of that submatrix. But if it is 0, then move to smaller submatrices and repeat the process till you get the rank. Next is analysis of a system. So if rank of the augmented matrix is not equal to the rank of the original matrix, then it is an inconsistent system and it doesn't have any solution. But if the ranks are equal, then it is a consistent system. And also the rank is equal to the number of variables, then it has unique solution. So solve it further, solve the equations simultaneously and find the solution. But if the rank is less than number of variables, then it has infinite solutions. Then put free variable and solve. Next is finding lambda or mu. So consider the matrix representation. Form the augmented matrix, convert to echelon form. Then consider the given cases, that is no solution, unique solution or infinite solution, and find the values accordingly. Next is to check if a given set is a field or not. So for that there are a few conditions. The first is closure under addition and multiplication. So suppose two elements x and y from a set, so their addition and their multiplication must be in that set itself. Then commutativity in addition and multiplication. So if for two elements x and y in a given set, x plus y should be equal to y plus x and xy should be equal to yx. Next is associativity. So x for three elements x, y, z, x plus y plus z should be equal to x plus z or x plus y plus z, just like real numbers, and similar for multiplication. Next is the distributivity in addition, that is x into y plus z should be xy plus xz. Next is to check if identity elements exist, that is 0 and 1. So why are these identity elements? So 0 is because any element x in the set, when added to 0 element, gets the element itself, that is x plus 0 is x and x into 1 is 1, x into 1 is x, sorry. Then we need to check if additive and multiplicative inverse exists. Here the answer is 1. So minus x and 1 upon x. So here x plus minus x should be 0 and x into 1 upon x is 1. So these are all the conditions you need to check to prove whether a given set is a field or not. Okay. The next part is to check if it is a vector space or not. So here are 10 conditions. First is closure in vector addition. So suppose there are two elements u and v of a given set V, capital. Okay. So u plus v should be in V, that is closure in vector addition. Commutativity is again u plus v is equals to v plus u. Associativity we have discussed before, it's similar to real numbers. Then existence of zero element, u plus 0 is u. Existence of additive inverse, u plus minus u is 0. Then closure in scalar multiplication, so this one is important. So for any scalar in the field on which the vector space is defined, that scalar into the vector u should be in that set itself. I mean that suppose u is in V, set V, and alpha is a scalar from the field K, so alpha into u should be in the set V. Okay, understood? Next is closure in scalar. Okay, that is done. Next is distributivity. So there are 3 points of distributivity. First is vectors in addition, so it is basically alpha into u plus v, so it is alpha u plus alpha v, right? Then distributivity of scalars in addition is alpha plus beta into u, so it's alpha u plus beta u. And for scalars in multiplication, it is alpha into beta into u, so it can be alpha into beta into u or beta into alpha into u. If you know, you know. Okay, then next is the last is existence of one element, which is nothing but u into 1 should be equal to 1. Next topic is vector subspace. So you, for set to be a subspace, it should be a vector space itself, right? But you don't need to prove all the 10 conditions mentioned above. You just need to prove the first and the 6th condition, that is closure in vector addition and closure in scalar multiplication. Those are enough. Here I have mentioned these points in the previous video itself, but I have mentioned it again, sorry. So a vector space is a subspace of itself, and 0 is a vector subspace of every space. Okay, next is to find span of vectors. Okay, so first take any arbitrary point over the field, okay, over any field on which the vectors are from. So if the vectors are from R2, then take any point from R2, not from the set itself, right? Then show it in terms of the given vectors. So if it can be represented with the help of the given vectors itself, then the span is the set from which the point was taken. So for example, we have a set of standard bases of R2, right? 1 0 and 0 1 is the given set, and we need to find its span. So we will take any arbitrary element from R2. So for example, A1 A2, right? So we need to show A1 A2 in terms of 1 0 and 0 1. So how we will do it? We will basically just do A1 A2 is equals to A1 into 1 0 plus A2 into 0 1, right? So we can show it in terms of the given vectors. So that means that the span of the given vectors is R2, which is true, right? It is a standard basis because it spans R2. So the next is how to check for linear independence or dependence. So first consider the dependence relation, alpha 1 u1 plus alpha 2 till alpha n is equals to 0. So when we solve this relation, if all the values of alpha I are 0, then the given vectors are independent. But if there is at least one alpha I which is non-zero, then the given vectors are dependent. Okay, so independent all alpha I 0, dependent at least one alpha I non-zero. Moving further, to check if a set forms a basis or not. So as we discussed before, take the same example, right? 1 0 0 1. So how did I know that it forms a basis over R2? Firstly, the vectors in that set are linearly independent and they span R2. So they form a basis of R2. That's how you find it. You just need to check if the vectors in that given set are linearly independent and span the vector, not or, and. So they should do both. If either one is not satisfied, then it is not a basis. The next is to find dimension of a vector space. So this is pretty easy. Dimension of a vector space is nothing but the size of a basis or the maximum number of independent vectors, linearly independent vectors possible, or the minimum number of spanning vectors. So that's how we find it. Moving further to the next chapter, which is linear transformations. First is to check if it is a linear transformation. So we need to consider two arbitrary points in the first vector space and a scalar in field K. Then we need to check if these two conditions are satisfied. If both are satisfied, then it is a linear transformation. But if either one is not satisfied, then it is not a linear transformation. And an easy method of showing that it is not a linear transformation is to just take a counter example, right? Instead of doing the entire process for both the conditions. I mean, you can just know by looking at the transformation whether it is a linear transformation or not. Like, if there are like x1 into x2, then it is like obviously not a linear transformation, right? The next is to find transformation for 2x or 3x of an image. So here we need to consider standard basis, find their images, then show arbitrary point in terms of these, and it gives the linear transformation which is required. So basically, you will take the standard basis element. First, you need to draw a rough sketch of what you are actually doing, right? If you are using 2x operation, right? Then first you need to show before image where you show the standard basis elements which are 1, 0 and 0, 1 for R2. Then after you do this transformation, you get the image of 1, 0 as 2, 0 and 0, 1 as 0, 2, right? So with the help of these images, you find image of any arbitrary point, right? By using tu is equals to alpha 1 v1, right? That, yeah. So after finding alpha and beta and all the constraints, basically, you find the matrix representation, which is the required transformation, right? The next is to find kernel of kernel of T. First, write the definition of kernel, then consider an arbitrary element. So, since we need this element to be in kernel, assume that its image is 0, then we will get a matrix representation, right? So convert it into echelon form and find solutions. So the solutions are the elements of the kernel. Now to check if the transformation is 1, 1 or onto. If the kernel is 0, then the transformation is 1, 1. But if it is 1, 1 and both the vector spaces have same dimension, then it is onto. There is one more method of telling this which we will discuss now. Okay, so first we will discuss the matrix representation. Yeah, this is important. So consider the elements of the given basis as some vectors for simplification, then find their images with respect to some constraints, right? Then find these constraints and get the matrix representation. The constraints should be as rows and not as columns. Oh, sorry. It should be as columns and not as rows. Sorry. Then we need to check if it is invertible or not. Right. So to check if a transformation or the matrix representation of a transformation is invertible or not, you just need to find its determinant. Okay, so if the determinant is 0, then it is not invertible. But if the determinant is non-zero, then the given transformation is invertible. Now this is the important method. So if the determinant or the row echelon form is has full column rank, then it is 1 1, and if it has full row rank, then it is onto. Okay. Then this is the example which we have discussed before, but still I will discuss the algo. So if images of specific elements are given, like suppose this is given, u1 is an element, its image is i1, and so on, then the elements will form a basis. Then consider any arbitrary point and represent it in terms of these elements. Then find constants and resubstitute, and hence get the required transformation. Now, from the last chapter, there is only one thing that is worth discussing again, which is to find any transformation like rotation, reflection, any transformation, any kind of transformation. First, draw a rough diagram, obviously. Then consider the standard basis, right? Then find their images. I feel like I have discussed this before, but still. So find their images using the diagram, then represent the images in terms of the standard basis elements, find the constants, and get the matrix representation. So that is how you find any given transformation. So this is basically kind of a summary of the entire all the 3 videos which we have discussed before. I will be including the link of this PDF in the playlist, or probably below this video. Yeah, somewhere I will do it. So thank you for listening, and I hope these videos are like useful. Thank you.